Bismillahirrahmanirrahim. Good evening, ladies and here in our conference room, in our Zoom, in our YouTube. Assalamualaikum warahmatullahi wabarakatuh. Thank you so very much for being with us this evening in Bandung, elsewhere in the morning, in the afternoon, in the very late evening. Thank you very much for being with us. Welcome to the symposium, which has a very perhaps unusual title, From the Universe Back to Earth, Developing Astronomy to Meet Today's Natural Challenges. This symposium is planned as one of the chain of programs that we arrange for the celebration of the century-old Bosscha Observatory, one of the oldest modern observatory in the Southern Hemisphere. We are happy to report to you as an organizer that this symposium, even though this is a new endeavor, creating a pavement to have astronomy a better contribution to the modern challenges, be it in climate change, be it what we just experienced in the past years, the pandemic, and other various conflicts that we are facing today. It is important that astronomy is one of the developing science, one of the very popular science, lend a concrete hand into meeting all these challenges. And we have seen in the past decade that colleagues from various institutions in the world have tried to use astronomy facility, knowledge and skill to lend it to other fields that perhaps not even foreseeable by us in astronomy. So we'll see some of them in this symposium. Here with us, participating in this symposium are about 50 people and 16 invited speakers representing 16 countries in the world. So I think this is a very exciting time, even though this is a new endeavor. People undoubtedly are interested to learn, interested to contribute, interested to work together. So I'm very, very pleased with this. So thank you very, very much in participating in contribution and willing to come to discuss what we are learning while facing these new challenges. Without further ado, I would like to invite our Dean, Professor Wahyu Sigutama, who is here with us, the Dean of Faculty of Mathematics and Natural Sciences, to say greetings for you. And after that, we will listen to the opening remarks by the Rector of Institut Teknologi Bandung, and then we'll continue to listen to the keynote lecture, which I will explain a bit later. So, Pak Dekan.
Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. May peace be upon us all. Good evening, everyone, and welcome to the From the Universe Back to Earth, Developing Astronomy to Meet Today's Natural Challenges. We are honored also to have the Rector of ITB, Professor Reni Wirhadi Kusuma, who will be presenting her opening speech for tonight. And this symposium is an opportunity for us to explore the latest development in astronomy and how they can be applied to address the natural challenges we face today. Thank you also for the to Professor Jan Fischer for your being here again with us. It's a great honor and also to all the professors, the guest professors, also the lecturers, the students, all researchers who are participating in this event, both offline here in this room and also in Zoom and YouTube, I suppose. And we will have a great lineup of speakers and presentation, including a keynote opening lecture by Professor Timothy Palmer from Oxford University on the geometry of chaos, primacy of doubt. As we gather here at Ganesha Campus, Institut Teknologi Bandung, we are reminded of the importance of scientific research and innovation in addressing the challenges of our time. The Ministry of Education, Culture, Research and Technology has supported the development of astronomy research in Indonesia, and we are grateful for their continued support. Especially this year, we are entering the 100 years of Bosscha Observatorium. As we delve into the latest developments in astronomy, we are also reminded of the challenges that come with the scientific progress. Mathematical physics has been instrumental in answering many of the challenges that have arisen as science has developed. Throughout this symposium, we will explore the tools used in astronomy research and how they can be applied and address the natural challenges we face today. We hope that this symposium will inspire new ideas and collaboration that will help us to better understand the universe and our place in it. I think that's my simple speech, I think. And of course, I want to, on behalf of the Faculty of Mathematics and Natural Sciences, I would like to express my sincere gratitude and highest appreciation to Professor Nana and team for arranging this event. And again, thank you for joining this event, and I hope that you enjoy the symposium. Wassalamualaikum warahmatullahi wabarakatuh. Thank you.
Thank you, Dean, Professor Sigutomo. With this, maybe we could start the speech by our rector, Professor Raini Wirahadikusuma.
Hello, everyone. Assalamualaikum warahmatullahi wabarakatuh. Greetings from Institut Teknologi Bandung. The year of 2023 is very special for our colleagues in astronomy in Indonesia. First, it is the centennial year of Bosscha Observatory, one of the first few large modern astronomical observatories in the Southern Hemisphere. It is still active and should be ready to embark on its new mission. The second, Indonesia had the fortune of having a total solar eclipse pass on its eastern part on the 20th of April. Institut Teknologi Bandung arranged for a year of astronomy activities with various aims, including for public at large. It is a unique time for astronomy to get attention, as well as to show how it has been a contributing factor to the development of civilization. This symposium strengthens the motivation to identify knowledge and skills in astronomy and also in astrophysics that push our contribution to saving Earth, strengthen collaborative networks that will expedite the achievement of the motivation. The various topics in the proposed symposium cover details of science developed in astronomy and astrophysics that could be useful in investigating and understanding the Earth as part of the solar system, of course, but also as a unique planet. This idea has inspired a number of astronomical projects around the world to invest significant portion of their projects to study Earth, which are now developing into interesting projects in their own rights. With the challenges in understanding various natural phenomena on Earth we are currently facing, it is imperative that we lend our knowledge in astronomy and astrophysics, our facilities, technologies, and tools to increase our understanding of the Earth and work together with a wider field of expertise in order to construct a collaborative effort to care for our Earth. The reason that make astronomy appealing to all, including the young generation, are precisely the ones that make astronomy a good entrance to science, technology, engineering, arts, and mathematics, or we call STEAM education. Astronomy is universal. It is inspirational, relates to all sciences, pushes technology forward, and invites people to reflect. Those reasons are woven to construct the goals of learning STEAM via astronomy, which are, the first is to raise awareness, raise comprehension of the physical world and natural causal relation. The second, astronomy can promote rational perception and respect towards abiotic and biotic environments, including human beings. Third, promote curiosity, knowledge, skill, creativity in STEAM. And fourth, promote positive participation and mindfulness. These four goals resemble and emphasize the key spirit of Sustainable Development Goals. I learned that the SOC members and the invited speakers of this symposium, representing various STEAM elements and world regions, bring in your respective expertise, experience, network, reflecting the coverage of the subtopics that embed the goals. This symposium will also accommodate learning experience from works at the interface with relevant public and education sectors. Institut Teknologi Bandung is one of the few technology institutes which also house science and arts. I am very, very pleased that science, technology, art, education, and public services are pushed forward to understand and take better care of Earth, which is our home. In addition to that, hosting the symposium in a university setting allows the message to reverberate effectively across academia, which has the duty to develop the content into knowledge, skill, application, and indeed competent human resources. I thank the scientific organizing committee, the local organizing committee, invited speakers, especially all participants who join us from all over the world, and also the sponsors, and all who support this symposium here in Institut Teknologi Bandung. I would like to especially thank Professor Timothy Palmer of Oxford University. Apologize, I cannot meet you face to face, who will kindly give us a very important and most relevant opening lecture right after this. I wish you all a wonderful, meaningful symposium and all best wishes in embarking on this new invaluable endeavor. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
We thank Professor Reni Wirahadikusuma, our rector, for giving us a very kind support and remarks for this opening. So we feel that it is an endeavor that the Institute Teknologi Bandung is also acknowledged and support, and also for the it is a part of the celebration of the 100th year of Bosscha Observatory. So we are very grateful for her presence here. The next, ladies and gentlemen, we will listen and learn from Professor Timothy Palmer. He's a physicist at the Oxford University, but who's been involved very much in studying the complexity of meteorology and everything else that is needed for us to be able to predict in a very complex dynamical system. And all of those requiring us to understand the existence of uncertainties and how to deal with uncertainties when we are in very dire need to predict. Now that we are living in a very complex world, in our relation among us, in our relation with nature, how we very much depend on nature for our well-being, it is very understandable that we need to be able to predict in scientific manner, but also in ways that all public would understand. Professor Palmer wrote a very beautiful book, in my opinion. It's called Primacy of Doubt, which is part of the title of his talk. I would invite you to read it. It's very thorough in its approach in mathematics and physics, but also makes it very relevant to what we are facing these days. So without further ado, I would ask our colleagues to start the lecture, and Professor Palmer would join us at about 7:30 our time. So thank you very much.
Hello, my name's Tim Palmer, and it's a great honor to be giving this lecture at this very special meeting from the universe back to Earth to celebrate the 100th anniversary of the Observatorium Bosscha. So I'm going to share my screen with my slides and get going straight away. So title of my talk is The Geometry of Chaos, the Primacy of Doubt. And I should say that pretty much everything I'm going to say is taken from a popular science book I wrote pretty much during the COVID lockdown period about the science of uncertainty across a range of areas, from climate change, quantum physics, and indeed economic forecasting, COVID forecasting, in fact, as well. But underpinning all this is my belief that whilst it's universally recognized that quantum mechanics and relativity theory were the two great theories of 20th century physics, I'm going to argue that chaos theory should be thought of as the third great theory of 20th century physics, and in particular because of the geometry of chaos, the fractal geometry, about which I'll talk during this lecture. Just to give a couple of examples of chaotic systems, here's a still of what's called a double pendulum, and there's a little light emitting diode at the tip of the arm, which is jointed in the middle, as you can see, and the time-lapse photography shows how irregular that tip moves. And this is a sort of quite a good example of a chaotic system. This is taken from my own office in Oxford. This is another example of a chaotic system, which I'll animate, which is basically a pendulum oscillating around 4 magnets. And I like to think of this as a very simple picture of the weather, in the sense that the weather has certain sort of preferred quasi-persistent states. You could think of them as like warm, hot weather maybe, or dry weather, or wet weather, or cold weather. In this case, the pendulum has stopped, but in a true chaotic system, it would continue to oscillate very irregularly between these 4 magnets, or 4 regimes. I'll come back to this later on. Now, the prototype equations of chaos are given on the left-hand side, and were discovered by the MIT meteorologist Ed Lorenz, who I knew quite well, incidentally. And he formulated a very simple, well, simple in the sense that it's just got 3 components. He formulated his 3-component model in terms of 3 differential equations for the time rate of change of the 3 variables x, y, and z. And you can see 2 of the equations are nonlinear. Now, I've shown a picture of Isaac Newton next to Lorenz on the top left there, because I think if you had shown if you'd shown Newton those equations, he would have understood pretty much what they were about. He obviously was an inventor of the calculus, so he knew what dx by dt and dy by dt and dz by dt mean, and he knew the concept, of course, of nonlinear dynamics. So he would have understood the equations, but he would have had no inkling whatsoever of the type of geometry that these equations produce, this fractal geometry, which is something I will talk about. So the geometry is an emergent feature of the equations. And in the talk, I want to argue that this geometry links the classical mathematics of Newton with the very modern mathematics and indeed groundbreaking mathematics of the great 20th century mathematicians, Kurt Gödel, Alan Turing, Andrew Wiles. And perhaps also, I'll argue at the end of the talk, there may be something to say about some of the very deep problems in 20th century physics to do with quantum foundations, and perhaps trying to formulate a theory of quantum gravity. So here we have Albert Einstein, Niels Bohr, and John Bell, the Irish physicist that invented or discovered, whatever the right word is, the Bell inequalities, which won the Nobel Prize for 3 physicists this year. So I'll come on to that at the end of the talk. I want to say why, just very briefly, why I think this fractal geometry links to these mathematicians. So let me just briefly say what they discovered. Kurt Gödel, famous Gödel's theorem, the set of mathematical truths is much larger than those truths that are provable by algorithm. And in my book, I try to argue whether, an idea put forward by Roger Penrose, whether this theorem is relevant to the issue of whether artificial intelligence really understands things. But I'm going to leave that to one side in this lecture. Alan Turing essentially found a kind of specific example of the more general Gödel theorem by studying a particular problem called Hilbert's decision problem. Basically, is there a way of formulating a procedure which could in principle decide whether any given mathematical problem was true or false, or maybe ill-posed? But Turing showed that can't be solved by algorithm, and hence it can't be solved by any computer, no matter how powerful. And the third example is Andrew Wiles's famous celebrated proof of Fermat's last theorem. So these are three great theorems of 20th century mathematics. What have this got to do with the geometry of chaos? Well, let me start by illustrating what happens if you integrate these equations in the state space of the Lorentz system. So we've got three variables, so three-dimensional state space. And you start with some initial point in the state space and integrate the equations forward, maybe using a computer. And you see a trajectory in state space. It's a deterministic trajectory because the equations are deterministic for a sort of short period of time. But if you carry on for a long time, then you start to see a certain shape or geometry emerge from these equations. And this was the question which Lorentz, I would say, agonized over for a long time. And this was his real contribution, I think, in this field, to understand what this geometry was. He argued it couldn't be a three-dimensional, some sort of three-dimensional object, because the equations had some explicit time irreversibility, and it could be shown analytically that the volume of any kind of asymptotic geometry that these equations produce would have to be zero. On the other hand, it couldn't be a simple two-dimensional surface, because then you wouldn't get kind of exponential divergence of trajectories without violating the determinism assumption. But as I mentioned, he agonized about this and concluded after a while that this must be an example of fractal geometry. This is just a quote from his paper. We see that each surface is really a pair of surfaces. So when they appear to merge, there are really 4 surfaces. Continuing this process for another circuit, we see there are really 8 surfaces. And we finally conclude there's an infinite complex of surfaces, each extremely close to one or the other of 2 merging surfaces. This infinite complex of surfaces we'd now call a Cantor set of surfaces, after Georg Cantor, 19th century mathematician, who was the first to really understand the importance of fractal geometry in mathematics. So we can come back then to these 3 mathematicians, and for the first 2, I want to refer to some work by a mathematician, Simon Dubé, in the 1990s, who essentially showed that uncomputable problems such as the Hilbert's decision problem can be reformulated in terms of geometric properties of these so-called fractal attractors of dynamical systems. And hence the undecidability of Hilbert's decision problem is essentially can be recast in terms of the undecidability of geometric properties of these fractal attractors. So in some sense, the geometry of fractal attractors provides a geometric reformulation of the whole kind of Turing computability problem. And as far as Andrew Wiles is concerned, people may or may not be aware that in number theory, the mathematicians frequently use 2 different types of number system. One is the regular rational to real numbers. The other are p-adic numbers, which are essentially another way of completing the rational numbers with a different type of metric. And it turns out that the p-adic metric is very closely linked to the fractal geometry of Cantor sets. So the difference between p-adic numbers and our more familiar real numbers is really completely isomorphic to the difference between Euclidean geometry of spheres and so on, and fractal geometry. So again, we see through these fractal systems a link to some of the very deep ideas of modern number theory. Okay, now I'm going to continue looking at the Lorentz system, because I want to point out something that is not typically pointed out. I think everyone, no, everyone say everyone, I think, you know, all scientists and many in the public are aware of the so-called butterfly effect. And they're aware perhaps that chaotic systems are inherently unpredictable. But that is a very kind of crude characterization of chaos, because what we see here is that in fact certain parts of the Lorentz fractal attractor, this asymptotic geometry that emerges from his equations, certain parts of it are very predictable, certain parts are sort of moderately predictable, and certain parts are very unpredictable. So we're seeing here a little ring of points on the top left. You see it makes a transition from the left-hand part of the attractor to the right-hand part with actually very little, in fact, no divergence of or growth of this initial ring of points. You can think of the initial ring as representing some uncertainty in where the exact starting condition is. The top right shows, the top right shows that you can start to generate some uncertainty if the trajectories start kind of propagating down the middle of the attractor. And the bottom one shows that if you start kind of close to the bottom middle of the attractor, then you can get really dramatically growing uncertainty. So in chaotic systems, some states are actually very predictable, others not. You know, a big part of this talk will be to talk about ensembles of forecasts as a way of providing estimates, prior estimates of state-dependent predictability. I just want to say that this idea of sort of what I call intermittent instability is pretty generic, actually. And I want to illustrate this with a very nice example of the gravitational, this is actually gravitational four-body problem, which kind of, in fact, acknowledges the fact that in the early 20th century, Henri Poincaré really made some of the first most important steps in understanding chaos theory. And he looked at, you know, the gravitational three-body problem, but this is a nice example. I'll just show it to you now. We've got four gravitational bodies. There they go. And they're evolving around each other in very nice, seemingly very stable ellipses, very boring, nothing's happening. Oh, until suddenly an intermittent instability is triggered and the objects diverge off to infinity. It's such a nice example. It's worth showing it again. Here they go. They're just, you know, seemingly very predictable. And you might imagine, you know, training an AI system on this and it would say, oh yeah, it's predictable forever. But actually, no, it hits this instability and becomes extremely unpredictable. Well, you know, this is something I've worked on in the context of weather prediction and extreme weather prediction. And I just want to show you three examples of tropical cyclones or hurricanes, an actual forecast ensembles for these three cyclones. So the top one is one that they're all from a few years ago now, but one that hit Bangladesh. We're looking at about a 5 to 7 day forecast of an ensemble of tracks of forecasts. And on this timescale, I think one would have quite some confidence that a cyclone would be hitting Bangladesh a week or so into the future. This is, the middle one is what I would call sort of semi-predictable. This is actually the famous Hurricane Katrina that hit New Orleans. And at this range of several days out, there's actually, I mean, you can see there is some considerable uncertainty. In fact, if you look carefully, it's a little bit bimodal, but there's considerable uncertainty about where the hurricane will be hitting on the Gulf of Mexico, or indeed just running up the coast of Florida. And this bottom one is called Nadine, where, you know, the direction, whether it's going to the east or going to the west, is completely unpredictable. So this ensemble forecasting has now become fairly standard in meteorological offices and forecast centers around the world. And one thing that it has done is change the way in which disaster preparedness agencies operate. So in the past, where there were only single deterministic forecasts, disaster relief agencies really couldn't afford to take precautionary action. They couldn't really afford to send food and medicine and shelter and so on to a region that may be stricken by an extreme event, because the reliability of these deterministic forecasts was so poor, and they all have limited resources, so they would go bankrupt very quickly if they responded to every single case based on a single deterministic forecast. But the ensemble gives them an objective way of deciding when to take anticipatory action. And the basic idea is that you use the ensemble to calculate the probability of some extreme event occurring in a particular region. And based on a cost-benefit analysis, if you like, that the agencies would have done ahead of time, they can determine a probability threshold above which it is worth taking anticipatory action. So, if the probability exceeds 70% or something, let's say, then they would use that as a trigger to take precautionary action. So to go in and distribute, as I say, food, water, maybe finance, and so on, shelter ahead of time. And as the news article shows, this is really changing the way we manage disasters. So this is where being able to forecast uncertainty has made a real difference in the way in which society is being helped by science. It's making people's lives hopefully better by taking away the worst effects of severe weather for which they are completely vulnerable and have no means of protection. In the book, I talk a lot about ensemble weather forecasting. It's something I've worked on for many years, but I try also to, there are chapters on COVID. In fact, the epidemiological community actually borrowed a lot of ideas from the meteorologists to develop ensemble COVID prediction models, estimating the probability of death and hospitalization as a result of different potential policy measures on how restrictive interaction between people would be according to political intervention. Economic prediction, I would say, is slowly advancing in the direction of ensemble prediction. But in the book, I discuss how we need more, let's call them advanced agent-based models to really explore ensemble prediction properly. And there are some promising examples in that direction, but I think it's still some way to go before this has reached the mainstream sort of governmental agencies for doing economic prediction. And I've got a chapter on conflict prediction, mainly because one of the great pioneers of weather forecasting, whose name was Lewis Fry Richardson, who was very much a pacifist, he worked during the First World War as an ambulance driver on the front in France and did a lot of seminal work in his spare time on numerical weather prediction. But after the war, he became completely disillusioned with defense and war and so on, and he decided to devote his efforts to predicting conflict, and made some important contributions there. So ensemble conflict prediction is actually, I would say it's still in its infancy, but is again another area where ensemble forecasting and importantly, trying to forecast the occurrence of these intermittent instabilities is going to be very interesting, see how that pans out. Of course, in economics, we have intermittent instabilities in terms of, global financial crashes. And a big question is, if you took the 2008 financial crash and you could run it with an ensemble forecast, how uncertain would the ensemble estimate that crash to have been? I discussed this in the chapter. In 2021, my colleague from Princeton, Suki Manabe, won the Nobel Prize for developing the first climate models, comprehensive climate models, I should say, and using them to do some of the first comprehensive modeling of CO2, impact of CO2. It's a sadness to me that Ed Lorenz never won the Nobel Prize. I think his work certainly deserves one as well, but he sadly died some years back now. But the point to make is that in climate physics, we use, as of course in all most scientific subjects, we use hierarchies of models. So I want to actually come back to the simple example I showed of the chaotic pendulum to sort of illustrate the difference between weather forecasting and climate forecasting, because this is sometimes confused. People sometimes say, oh, well, if you can't predict the weather more than a few days ahead, what hope is there for predicting the climate 100 years from now? But that's kind of to misunderstand the nature of the climate change projection. So what I'm going to do is represent climate change, our emissions of carbon dioxide in the atmosphere, by slowly pushing this wedge underneath the magnets. And you will see, not surprisingly, that it biases the statistics of the occurrence of the pendulum bob over the individual magnets. And as I say, think of these as weather regimes, perhaps warm weather, cold weather, wet weather, dry weather, something like that. So we'll see that this continues to be, in fact, let's do it now, the system continues to be chaotic in the sense that the motion around the magnets is very unpredictable and would be sensitive to precisely where the starting conditions are. But what you can see, I think, just visually, is that the yellow magnet at the right-hand side is kind of becoming visited more frequently than the others. And there it goes. It actually ends up resting there. But in some sense, what we've done is to bias the statistics of the weather regimes. And that's essentially the problem that we're trying to tackle in climate change as we increase carbon dioxide level. How are the statistics of weather changing? And of course, that will vary from one country to another. Some countries will find that the dry, hot weather becomes more likely. Other countries may find that very wet, stormy weather becomes more likely. And of course, that's super important if you're trying to devise a strategy for adapting to climate change, to know what types of weather you will experience and with what probability in the future. And really, that kind of question can only be answered with very, very complex climate models right at the end of the spectrum where Manabe was. One thing to say is that with a complex weather forecast model, we're trying to solve the equations of fluid dynamics, and top amongst them is the Navier-Stokes equations for essentially Newton's second law for a fluid. And these are very well, they're simple equations from a mathematical point of view, but they're complex equations to solve numerically because they are not 3, 4, 5, or 6 dimensional they don't have a 3, 4, 5, or 6-dimensional state space, but an infinite dimensional state space. And the infinite dimensional state space is consistent with the fact that in a turbulent fluid, you have a whole spectrum of scales. And in fact, you know, there are certain scaling symmetries in the equations, which basically mean you have something like a fractal, if you like, in physical space, where you zoom in to the turbulent fluid and you see structures that you saw on larger scales. And that's consistent with the energy spectrum having what's called a power law structure, in sort of linear structure in log space. Now, because of that, these are you know, difficult equations to solve, and on a computer you have to impose a truncation scale to the model. The truncation scale is typically determined by how big a computer you have. And in some sense, you are violating the scaling symmetry of the underlying partial differential equations by doing that. So how do you kind of mitigate against that error? And I've tried to argue for a number of years now that one way to mitigate this is to actually treat the unresolved scales, what we call subgrid scales, by noise. In other words, by stochastic equations. And I imagine there are lots of examples, perhaps in astronomy, galactic dynamics, and so on, stellar dynamics, where a similar argument maybe can be applied. In other words, the scales that you can't resolve explicitly should be treated stochastically, even though the underlying equations are deterministic. Your computational equation should be treated stochastically. Now, in climate forecasting, you know, we're really always pushing the envelope of what computers are able to provide. And one of the problems at the moment is that computers are incredibly energy profligate. And in fact, it's really how much energy or how much power is consumed when you run a calculation that sort of determines the limit of what can be achieved, and essentially, therefore, how small a grid scale you can afford. And again, I've been trying to argue, well, if your equations are stochastic, maybe we don't necessarily need our computers to be completely deterministic. Now, the reason for saying that is that there's quite an energy overhead in ensuring a computer, you know, runs bit reproducibly and is deterministic. Now, this is typically met by my scientific colleagues with some skepticism, the idea that computers, we don't need computers to produce exactly the same answer if they're run twice, you know, is met with some incredulity. For a number of years, I've been sort of thinking about, well, are there examples in the natural world, if you like, where nature, as it were, embraces this notion of stochasticity and noise? And it seems to me one example is actually the human brain. We have about 80 billion neurons in the brain, and they are run not with 20 megawatts, which is what a modern supercomputer uses, but 20 watts. 20 watts, so 6 orders of magnitude less than a modern supercomputer, and the brain does an extraordinary amount of information processing with that 20 watts. But with such a small amount of energy power, noise and with the neurons having such, you know, tiny diameters, then noise is an inevitable consequence. And, you know, I think it's fairly unquestioned now that you know, there is noise in the brain. The way the brain works is susceptible to stochasticity, or can be at least. But I've tried to argue, and I argue in the book, I've written a few papers on this, but in the book I've tried to argue that actually this noise may be helping us, and in particular helping us become the creative species we are. And, you know, if you think about this from perhaps an algorithmic point of view, if you think about coming to, you know, a solution to a problem, to be somewhat similar to finding, you know, let's say the global maximum of some objective function, then in modern computer science, a lot of the most efficient algorithms for finding the maxima of objective functions are in fact stochastic algorithms. And there's a very famous one called the simulated annealing algorithm, which essentially uses noise in a constructive way to get to the maximum, global maximum of an objective function, where, you know, a more, let's say, deterministic algorithm might kind of get stuck and hang at some, you know, non-global maximum, at some local maximum. Anyway, I'm going to pass over that. So I just want to flag the fact that I think for complex systems, then nonlinear. Sorry, I just need to check. Yeah, nonlinear. I just need to check the time I've been speaking for. That nonlinear systems can make use of noise in a constructive way. Okay, sorry. So I just want to come on to the last topic here, which is certainly controversial, but something I personally believe in. And I should say I've been working in climate physics for many years now, but I did my PhD in Oxford in general relativity theory. And I have an enormous admiration for Einstein and his extraordinary insight into developing our current best theory of gravity, which is a deterministic theory in which events in space-time are objectively real, and in which there is a law of causality whereby signals essentially don't propagate faster than the speed of light. Now, in terms of quantum physics, so Einstein, you know, brought his beliefs into the quantum world by the famous statement, spooky, you know, no spooky action at a distance, and God does not play dice, this sort of thing. But modern physicists think he was wrong to bring those ideas into quantum physics. The Nobel Prize this year was given for three experimentalists who showed that Bell's inequalities, I'll speak about that very briefly in a minute, were violated, and it's believed that this violation of Bell's inequalities proves that the universe, to quote Scientific American, that the universe is not locally real. So what does that mean? It means either that Einstein's ideas about causality are breaking down, somehow quantum signals are propagating at sort of infinite speed from one part of the universe to the other, which is bizarre, or that, you know, that the world somehow is not, the notion of reality doesn't sort of somehow mean anything in an objective way, which is equally, I think, bizarre. I just want to actually just very briefly describe the experiments that these three Nobel laureates did in a kind of simple way. And they involve, as many people I'm sure know, entangled particles, pairs of entangled particles, which are emitted from a source. They propagate in opposite directions. And the polarization of the, let's call them photons, the polarization is measured by Alice on the left-hand side and by Bob on the right-hand side. And in principle, Alice and Bob could be light years apart. Now, Alice and Bob, the way the experiment's set up, Alice and Bob have two choices of, well, actually one choice each of how to orientate their polarizer. So Alice can orient her polarizer in one direction or in a different direction, and Bob can similarly orient his polarizer in one direction or a second direction. There are four directions altogether. Now, for the sake of argument, this is not the way it works, but in practice. But let's just keep things simple. you could imagine there are sort of 4 parts to a Bell experiment, and we could imagine them being done on different days of the week: Monday, Tuesday, Wednesday, Thursday. So I'm not saying this is actually how it happens, but let's imagine just for conceptual clarity. So on Monday, Alice and Bob measure with one of their choices. On Tuesday, Alice keeps her choice fixed. Bob changes his choice. On Wednesday, Alice changes her choice. Bob goes back to his original choice. And on Thursday, they both have their second choice. And each day there's an ensemble of entangled particles. Basically, for each choice of polarizer, a particle is kind of measured up or down relative to the polarizer direction. And so we get statistics of the correlations between the spin of the photons in these different directions. So there are four sub-ensembles, there are 4 correlations. What happens is that a certain combination of the correlations they satisfy this inequality, and the idea is that it would be impossible for, I mean, this is what Bell showed, it would be impossible for a traditional deterministic model to satisfy this equality without some kind of spooky action at a distance, or perhaps saying, you know, well, I say deterministic, so by a deterministic model, I do mean one where there are definite real, you know, experimental outcomes. Everything is kind of classical in that sense. Now, if you go through carefully the experiment, it turns out that there is an additional assumption. And I can put it like this: if we consider the particles whose spins were measured on Monday, we can ask the question, could these same particles have been measured with Tuesday, Wednesday, or Thursday's polarizer settings? So in other words, the second bullet is talking about counterfactual measurements that you might have done, but you didn't actually do. And the question is, are there theories where these types of counterfactual measurements might be inconsistent with the laws of physics? And if it's possible to come up with a viable theory where counterfactual experiments like this are inconsistent with the laws of physics, then actually we can explain Bell's experiment without having to invoke what I would call incomprehensibly weird ideas about action at a distance or indefinite reality. Now, most physicists would not view this idea of counterfactual worlds as at all controversial. And a very simple example, you can imagine, you know, in the real world, the boy throws the ball to the father. You could ask the counterfactual question: if the child had thrown the ball with half the initial velocity, would the ball have reached the father? Well, we have a deterministic formula from Newton's laws, which we could use to calculate how far the ball would go if it was initially projected with half its velocity compared to the real world. And Newton's laws will tell us, in this case, that the ball wouldn't reach the father. And so the normal view is, oh, well, counterfactuals are kind of, that's part of physics, so we can't possibly deny the notion of counterfactual definiteness. But this is where I want to come back to chaos and think about Lorentz's picture on the largest possible extent, which is to imagine that the whole universe is a deterministic dynamical system evolving on some cosmological fractal attractor. So this is taking an idea from Earth physics and applying it to cosmology. Now, the important point here is that because of the Gödel-Turing theorem, there is no formula for this fractal. I can't plug into a computer a formula to tell me whether a putative point in state space lies on the attractor or not. So let's imagine we do this experiment Monday, Tuesday, Wednesday, Thursday. By construction, according to this hypothesis, the real world, lies on a trajectory of this attractor. So the Monday, Tuesday, Wednesday, Thursday are kind of points, if you like, on the attractor. But now I want to consider counterfactual worlds, for example, where Monday's particles were measured on Tuesday, Wednesday, or Thursday, with Monday, Tuesday, or Wednesday or Thursday's polarizer setting. So I've got to slightly perturb these initial points. And I'm going to zoom into this. And you see, I've deliberately drawn this so that Wednesday's counterfactual world lies in a fractal gap. Now, if that's the case, then we actually have a mechanism to explain Bell's experiment without invoking non-locality or determinism. And I've written about this in a number of papers, which I won't go into now. But I think there is a kind of an important message behind this, which I feel, I don't know whether it should appeal to astronomers, I think, hopefully. You see, the point about the Lorentz attractor is that it's a very holistic structure. It's a holistic geometry. You can't just take a little bit of it and kind of define it from a little portion. You have to know the whole structure for it to make sense. And in some way, this goes opposite to the kind of usual ideas about spatial reductionism in physics, that, you know, if we want to understand, I don't know, quantum gravity, we have to probe smaller and smaller scales. We have to get down to the Planck scale or something like that. And I think this interpretation of Bell's experiment is actually telling us that it's this assumption, not non-locality or indeterminism, it's this assumption about spatial reductionism that may ultimately be wrong, that you know, the large-scale structure of the universe could actually be as important for determining the structure of the laws of physics at a really deep level, you know, as the physics of the Planck scale. And my view is it's a little bit like looking at that picture of the Escher drawing and saying, well, I'm going to, you know, to really understand that picture, I'm going to zoom in to a very, very small part of it and analyze that in great detail. Well, okay, I mean, if you zoomed into one of the hands, you would perhaps learn something about how Escher, you know, drew these drawings, you know, in his kind of graphical technique, but it would tell you nothing whatsoever about the meaning behind that picture. To see the meaning, you have to zoom out and see the whole thing on the large scale. And I think that's what we're sort of missing in fundamental physics, and why, in my view, it's been so difficult to come towards a theory of quantum gravity. Okay, so I'm going to finish. I have 1 minute, so I can just very quickly review. I think the most perhaps important thing is that, you know, being able to quantify uncertainty is really a defining characteristic of the scientific method. The title of my book, The Primacy of Doubt, the word primacy means that, you know, it's as important, if not more important, to define uncertainty as anything else in one's calculation. I think that's super important, no matter what area of science you're in. If you can't quantify the uncertainty in your predictions, then you're not being scientific. And the second point is to note that chaotic models are not necessarily strongly unpredictable all the time. Frequently, unpredictability is confined to periods of intermittent instability. We see this not only in weather, but in the economy, in our health, et cetera, and in the motion of planets and everything, you know, asteroids and so on. Ensemble methods have been developed in weather and climate forecasting to provide prior warning of periods of intermittent instability. It's got enormous practical benefits, and these are beginning to be used in other fields as well. When we have complex chaotic systems with infinite dimensional equations, and we want to represent them computationally, then noise is a very useful way of representing unresolved scales. And noise has many constructive benefits in nonlinear systems. It's not the nuisance that we typically think it to be when we think in a linear way about signal to noise. And it may, in fact, be the key factor in the brain in making us the creative species we are. That's my view, at least. So in conclusion, then, I'm trying to sort of argue that, and I talked a little bit about quantum physics, and I'm trying to make the case really that the chaos theory is up there with relativity and quantum mechanics as one of the three great theories of 20th century physics, and that, you know, Lorentz's insight into the fractal geometry of chaotic systems is really one of the great discoveries of physics. And I think it may, speculation of course, but I believe it may help us understand some of the very deepest mysteries of quantum physics, and in particular how to synthesize quantum and gravitational physics together. So that is the end of my talk. And as I say, I'm very grateful to everyone for listening. And I hope to maybe see you all in person at some stage in the future. So thank you again very much.
Hi, Professor Palmer. Would you
Hello.
be ready to take questions?
Sure.
Okay. So any questions from the room? There's one question in YouTube, I see. Yes, Pak Jaya. Hang on, just a minute. Let me.
Thank you, Professor Palmer. Your explanation seems unpredictable. Ordinary people used to think that a chaotic system is unpredictable. No prediction is possible. Is chaos theory can transform unpredictable system so that some prediction can be done, can be done from that system. Is that correct? Thank you.
Yes. Well, first of all, greetings from Bermuda, where I'm visiting my son, who's just had a child, our second grandchild. So so to answer your question, the point I want to make is that chaotic systems can be predictable for quite long periods of time. I mean, ultimately, if a system is chaotic, then it will ultimately be unpredictable. However, it's wrong to think that chaotic systems are completely unpredictable. And I mean, obviously, a good example is what Poincaré originally investigated, which is the solar system. I mean, we use the motion of the planets and the moon around the Earth and so on as kind of as clocks, because it's so reliable and predictable. But in the very, very, very long term future, even that can be unpredictable. So the issue really to make reliable predictions requires one to understand and to be able to quantify the sources of uncertainty in the prediction, and that can come from the initial conditions and it can come from the model equations. And then to be able to run ensembles of forecasts which sample those uncertainties. And with the ensemble, then you have a means of knowing in advance whether you're studying a predictable situation or an unpredictable situation. So, I think in general terms, pretty much everything, in our daily lives has limited predictability. And the key to success is to know in advance whether one is in the system that you're studying is in a predictable state or in an unpredictable state. And as I say, ensemble forecasting gives us that tool. But of course, it depends critically on being able to, first of all, understand, and secondly, quantify the uncertainties in the system. And that's often a non-trivial problem. And for example, in economics, that's probably where a lot of the challenge lies, in being able to properly quantify uncertainty. So I'm not saying it's an easy problem, but that's the way to tackle it, to treat uncertainty as a primary variable, as important as anything else, and not to treat it as a kind of an afterthought. Thank you.
Thank you very much. Any more questions from the room?
Thank you. Thank you, Professor. I would like to relate your conclusion number 1, 2, 3, 4 about the role of noise, since we comprehend that chaotic behavior solely depends on the non-linearity of the among parameters, and also the value of initial condition, and not on the noise or error in the input. So how do we comprehend your conclusion number 4? Thank you.
Yes, that's right. And in my book, I tried to distinguish between 2 different types of chaotic system. One, such as Lorenz's famous model, has a very small number of components, a number of variables, 3 variables. And it's relatively, straightforward now for, for a computer to solve the equations with just 3 variables. But on the other hand, you have systems like the climate system, which are effectively governed by an infinite number of variables, or at least a number of variables that is so large that even the very most powerful computers in the world cannot represent all of that complexity. So just think of climate. It comprises everything from planetary scale oscillations of the jet stream with scales of tens of thousands of kilometers, down to small gusts of air around a building or something with scales of centimeters or even millimeters. So there's no way you can represent all of that. And traditionally, what people have done is to truncate the equations. You solve them on a computer, you truncate the equations to a certain scale, let's say to 100 kilometers, and you try to find a simple formula to represent the bulk effects of all the processes that you have to neglect. The problem with this is that scientists have never been able to simulate the climate accurately with this type of procedure. And what I'm saying is that a better way to make progress with this problem, when you have a very large number of degrees of freedom, is to forget about, don't even try to think about that there might be a single deterministic formula which describes all of the unresolved scales that you can't represent explicitly, but instead treat the unresolved system by stochastic equations. So they have some inherent noise in them, and noise is a kind of a simple, but it's an effective way of representing very large numbers of scales that you cannot afford to represent explicitly. So I've spent a lot of my time developing these sort of stochastic climate models, and I could give a whole lecture on the benefits of noise. But we see it in other systems as well, and I think probably the most interesting of them is the brain, because the brain operates with 20 watts of power, 6 orders of magnitude less than a supercomputer. with 80 billion neurons. It is a noisy system. And I think the brain makes constructive use of noise, actually. And we see in lots of other cases, when you want algorithms to solve complicated problems. I mean, a good example might be the traveling salesman problem. People might be familiar with that. You can devise algorithms which can be very efficient for solving the traveling salesman problem, except that there are instances of the problem where any deterministic scheme will kind of become extremely inefficient. It's what's called the computer program kind of hangs because it just can't get out of a kind of a local minimum of this in solution space. And again, what computer scientists have found is that the most efficient algorithms for solving across a range of potential, traveling salesmen, potential network of cities are stochastic algorithms. These have, on average, the best performance. So I think, there are many, many, many applications of this. And my own personal view is that I know AI makes some use of stochasticity, but I think in future we're going to see a big explosion of growth of AI systems that build on kind of prior ideas generated by stochastic processes. So it's just a sort of long answer for a question that I think noise is really important and typically underutilized. I mean, my fantasy, by the way, for the future is that future computer systems will actually be noisy. And the fascinating thing is you can do that you can make a computer noisy by turning the voltage down across transistors. If you turn the voltage down, you're using less energy than you would have done when they were deterministic. So I think a pathway to future low energy supercomputing, particularly for systems which benefit from noise, nonlinear systems which benefit from noise, will actually be to create the noise in hardware by having low energy chips with extremely low voltages, much like the brain works with extremely low amounts of power. I think we can learn a lot in computing hardware by looking at how the brain copes with noise and how the brain deals constructively with noise. Thank you.
Thank you very much. I think I will read questions from YouTube. The first one, I think, relates to the previous one. Dear Professor, I have a question. If in the near future, quantum computers exist and the power more than 5,000 qubit, can quantum computers for weather and climate prediction will be accurate? Thank you.
That is a great question because I wrote a paper with a postdoc of mine whose name is Felix Tenney, and you can find the paper on the archive, and it was published by the Bulletin of the American Meteorological Society. It was precisely this question: will a future quantum computer, with whatever thousands of qubits, be able to solve the weather and the climate in an efficient way? And our answer was no. And the reason is for a reason which I do not find is discussed sufficiently well in the quantum literature. So let me explain why. You see, on the one hand, actually, you don't need 5,000 qubits. You need about sorry, I'm just trying to think now how many you need, maybe just 100 or so, because the size of Hilbert space it grows exponentially with qubit number. So if you want a few billion variables, you actually only need a few tens of qubits. You just exponentiate that number. So at first sight, it looks like quantum computers are going to be useful. The problem is that the problem is getting out information after the computation has finished. And, you know, if you think about a normal weather forecast, the weather forecast finishes, and then somebody might say, okay, well, what is the forecast for London or Jakarta or, you know, San Francisco? What is the temperature? So you write print temperature for London or something, and it'll print the temperature. Print rainfall for Jakarta, and it'll print the rainfall. This is not the way it works in the quantum computer. You can't do that in a quantum computer because the qubits represent spins which point in a certain direction. So, and when you do a measurement on a spin, it gives you the answer yes or no, up or down. The spin points in you ask for a spin in a certain direction, and the answer is yes or no, up or down. So it's very binary. In other words, you have to ask the computer a question where the answer is yes or no. So I think it's with 30 qubits, you can represent a billion-dimensional state space. So that's great. So you have a quantum computer with 30 qubits, and it forecasts the weather. Now you want to know what is the weather on, say, next week. So you say, okay, is it raining in Jakarta? And it'll come back, let's say, yes. Okay, fine. But now you've only got 29 questions left out of 30. Is it freezing in London? No. Okay, now you've got 28 questions. And so on. So you can ask 30 questions of this billion-dimensional state space. And this is completely useless for any practical, you know, weather or climate prediction system. You need to know the values of millions of variables, correlated variables around the world. Restricting to 20 or 30 it is pretty much useless. So this is the problem with a quantum computer, that it's not the calculation in Hilbert space is very, you know, exponentially efficient, but it's the measurement problem which collapses that vast dimensional Hilbert space back down to a small size, basically determined by the number of qubits. And this is a fundamental problem for anything that needs big data, where you have big data output. A quantum computer is not well suited to a type of problem that requires big data output. So for that reason, I'm actually skeptical that quantum computers won't replace ordinary classical computers. There may be niche applications where quantum will work, but it's not going to replace classical computers, and it's because of the problem of data output.
Thank you very much. There's still a number of questions on YouTube, but I will offer Jan to ask his question, one of our participants here in the room.
Thank you very much for sharing your thoughts.
I'm sorry, I can't hear.
Thank you very much for your thought. It's very interesting. It brought me back to the theme of this symposium, which is caring for the earth. Those who are supposed to have to play a role in caring for the earth, for the earth, is humanity itself. So we as humans are looking for ways to predict the future and how to interact with it, but we are ourselves part of the problem. So you spoke about the noisiness of complex systems. If there is one very noisy complex system, I think it's humanity. I wonder if you have comments on how say in a perspective, and that becomes quite clear at the moment, that humanity must change. The way we have grown to be in the world doesn't work because we are destroying our habitat in the world. You can't tell people simply, well, do so and so, and then the problem will be solved. So what is the way that we should go forward, in your view, from the perspective of your theory?
Okay, thank you for that very stimulating question. I think I would like to pick up on just, I mean, your question is very broad, and we could discuss it for a long time, but I'm going to pick up on one particular point which sort of relates to my book and my ideas. You see, I started my career, my research career, in general relativity theory. So I was very much in the astrophysics department at Oxford, I came into contact with many of the great physicists and cosmologists at the time, and then I moved into climate, and I found that many of the mathematical techniques that I had learned, and indeed the physics that I had learned, was applicable. And I like to think that such progress as I have been able to make in my field, in the field of weather and climate over the years, has been because I have been able to take ideas that perhaps originated in other areas, such as astrophysics, and bring them to bear in climate. So just to come to your point, I mean, I'm personally of the view that we have to embrace technology. The problem is a difficult one, because, as you say, we are damaging the planet. But on the other hand, we would like to get people out of poverty, people who, look at the very profligate ways that we in the West use energy and so on, and they aspire to our standard of living. And the question is how to do that in an equitable way. And I think that technology has to be a large part of the solution. But to make technological advances in a short time as well, we have to be prepared to get out of our silos. And I feel that not enough. If I had to kind of recommend one thing, I would say that governments around the world should be encouraging scientists and technologists to move fields. So, somebody who's done a PhD in astronomy should be able to move into earth sciences or into the sort of technological spheres that will help, I don't know, improve food production or water availability, or energy, low carbon energy, all this sort of thing. So if there is one thing I'd like to sort of come out from my study, it is that interdisciplinary thinking, is the way to get new ideas into a field. I mean, it's very rarely that an idea comes completely out of the blue. It's usually where somebody has transported it from one field to another. And so, but in some ways, I think actually, you see, I often think that if I, in the UK, for example, where I live, if I had just finished my PhD in general relativity last year, I think it would be much more difficult for me to move fields today than it was back in the 70s when I did it. Because these days, to become a postdoc, you have to have N publications, already at the end of your PhD, where n, can be a big number. And in some ways, I think this stifles our ability to move fields. So this is just one small part of what is a very complex problem that you're mentioning. But I do think in science, we need to find ways of making our scientists more mobile between fields, and people who I'm sure everybody in the room is also, like you, concerned about the issues of environmental degradation and climate change and all the rest of it. And I think they can provide, their expertise is valuable if they are given the opportunity, maybe it's only for a few years, but to move into these fields and see what can be done. So that would be my small contribution to this complex problem.
Thank you. A lot of things to really digest from there. But I think this symposium, in a way, aspires to do that in a small scale, to get people to know one another from various backgrounds. Astronomy may be the most interesting science, just to start with what we know.
We have to get the administrators as well to understand this. So it has to go high up into the governmental kind of structure of science funding.
Yeah, agree. Maybe I'll just read one or two more questions. We all need to get going with the evening and you with the day. One more, is it fair that when we talk about global view of things as a way to understand small things, it's analogous to the Weierstrass function, which is continuous, but its derivative doesn't exist?
Well, that's a very that's a very specific example. I mean, I'm not quite sure actually is the short answer to that, but I would rather take the analogy with I mentioned Escher. Another example is listening to a piece of music. Nobody would drill down into a small part of a Beethoven symphony to try to find the understanding behind that symphony. They would listen to the whole thing and try to view the structure as a whole. And I think, we've got to apply that type of maybe artistic thinking in the sciences as well. So that would be my answer.
Yes, we are always do the asymptotic estimation, then the universe will prove about it, like Ruqyatul Hilal and Hisab method. This is about observing the new moon method to determine new moon for Ramadan fasting period. But in a scale of universe, we know that as the slightest change of parameter will be big dominus effect of the other. Can we use the major calendar to determine the new moon in every month?
I'm afraid I didn't really catch that question properly, so I can't answer it.
The idea is about observing new moon.
New moon. Oh, well.
The Islamic calendar starts with Ramadan, for example, which is the well-known one. So if there are a bunch of parameters which is affecting the new moon, so what would be the idea of or elements of uncertainties or complexities in determining new moon every month?
Well, I mean, we do obviously have a very we have predictions of the new moon for many, many years. I mean, I remember as a child, so I'm talking now about the 1950s when I was quite young, reading that there would be a total eclipse of the sun in England, in southern England in 1999. And I found it amazing, actually, we could predict that far ahead. And I remember in 1999, I went with some friends, and in fact with my son, to watch the eclipse. And in fact, we went to northern France because it was clear that England would be very cloudy and we wouldn't see it. But northern France, the probability of cloud was also about 50%. And it wasn't until about, I would say, literally a few minutes before the eclipse that we knew we would actually see it. And it put into sharp contrast the predictability time of clouds with the predictability time of the moon, one being very short and one being very long. But even the moon, you see, is not completely predictable because, for example, we don't know about, the asteroid belt has limited predictability, and there's always a possibility that a sufficiently big asteroid could perturb the moon in an unpredictable way at some stage in the future. So all these systems are chaotic, whether it's weather, the solar system, the galaxy, everything, in fact, the whole universe. But of course, the timescale, each system will have its own characteristic timescale. But of course, what I'm arguing is that even when you have a characteristic timescale, that actually just represents an average of a distribution of timescales, which can vary from, relatively short to relatively long.
Great, thank you. I think that's eclipse illustration really is very, very enlightening. Would there be any other questions from the room? I think this is already quite long for you and also for us here. It's been a very, very happy occasion to have you with us, and thank you for being heroic, getting ready in the morning to be with us. We really, really appreciate this, and hopefully this is only the first day. Hopefully this is going to be a motivation booster for the next few days for us to meet. So thank you very much, and thank you very much for everyone here in the room.
Thank you very much. It's been great to talk to you all.
Thank you for everybody in YouTube and also in Zoom. So I think for us here, we will have dinner for you. So enjoy the rest of the day, and everybody else, perhaps in Australia, in Taiwan, in Japan, have a very good night rest. Thank you very much, everyone. So let's end here. So thank you again, Tim.
Bye-bye.
Bye. So I guess for us here, we can have dinner, and for everyone in Zoom, again, thank you very much. For all of you in YouTube also, thank you very much. Selamat malam. Wassalamualaikum warahmatullahi wabarakatuh.